is Arnett.
This is Judd.
Skyler.
We're gonna walk you over our Elct 201 lab project, which is digital filter for audio to drive LED string. The objective of our project is to interface and control an LED string using high pass and low pass digital filters with an audio signal being acted upon. The way our system works by taking 3 samples from an audio signal and converting them to a digital high and low pass by using respective equations and then turning on a corresponding LED. Here is a schematic of our entire system. As you can see from the top left, we have the speaker. One of the input of the speaker is going to the ground, and the other input of the speaker is going to the non-inverting input of the operational amplifier, which acts as a converter circuit. The reason behind using the operational amplifier is that to convert the mushy signal coming from the speaker to a square wave, going to the Freescale microcontroller, especially to the analog input BTB0. Then we have 2 digital outs, 2 digital outputs coming from the pins BTA13 and BTA4. BTA13 was used for the low pass, while BTA4 was used for the high pass, and each one of them is connected to the base of a transistor, which acts as a switch. The emitter of the transistor is connected to the ground, and the collector is connected to the light. And the reason behind using the transistor is that to prevent our microcontroller from the sinking current coming from the lights and sending a true zero.
The purpose of a filter is to remove unwanted parts of a signal and to extract the useful parts. There are 2 main types of filters, analog and digital. In this lab, we only utilize digital filters. A digital filter uses a digital processor to perform numerical calculations on sampled values of a signal. An analog input signal must be digitized using an ADC, analog to digital converter. This series of binary numbers is then transferred to the processor, which carries out numerical calculations. These calculations are typically multiplied by a constant and adding products together. These calculations are then outputted to the DAC, digital to analog converter, to convert the signal back to analog. The digital high and low pass filters can be achieved by 2 equations. The high pass filter is a central difference filter, which takes the current and the second previous input and subtracts them, then divides by 2. The low pass filter is a 3-term average filter equation, which takes the sum of the current and the 2 previous inputs and divides them by 3. Both of these equations create a number to represent frequency.
For our project, we use the Embed website as shown here, which is an online cloud-based compiler which allows multiple group members to collaborate on a single project from remote locations. The website was also very helpful when troubleshooting the code, as it has open source peer-to-peer sharing capabilities. This allowed us to see previous problems from other projects. The code starts by assigning input and output pins. This allows us to attach functions to specific ports of the microcontroller. The input will come from the speaker after it goes through the comparator circuit as shown previously in the schematic. The 2 digital outs, PTA13 and PTA4, will be used to interact with a blue LED for low pass filter and a red LED for the high pass filter. Next, we initialize an array to use as our memory location for X and Y values. As previously stated, the X values will come from the speaker and the Y values will serve as the equations to be compared within the low and high pass filters. After our storage locations are set aside in memory, the code will initialize the functions that will check low and high pass filters for the desired values. The low pass function will call .read to receive input from the speaker, which values are expected to be from 0 to 1, and take 3 iterations to be added together and divided by 3. This is a 3-term filter as discussed previously. If the value of y is greater than 0.3 and less than 0.5, the console will print low pass start, and a digital output of 1 will be sent through pin PTA13, which will cause the base of the transistor to go high and turn on the corresponding blue LED. Next within the code is a call to the function to check high pass, which will only be a 2-term average unlike the low pass filter. X2 will be subtracted from X0 and divided by 2. We decided to scale these values by multiplying by 2 powers of 10 because we felt that would increase the visibility of the incoming information to be extracted by the high pass filter. Since we scaled, we parameterized the function such that if Y1 is greater than 31, then a 1 will be sent from PTA4 to charge the transistor and turn on the corresponding red LED. Within the main, we will check values and print Y0 and Y1 to the console.
Here's a quick list of the materials we used for this project.
And this is how we decided to build the circuit.
Here are the input and output channels of our comparator circuit. Channel 1, which is the yellow, shows the audio signal going into the non-inverting pin of the op-amp. We can see that the voltage of the audio signal roughly oscillates between 10 and negative 10 millivolts, with occasional spikes in voltage. Channel 2, which is the blue, shows the output of the op-amp. As you can see, it makes a nice square wave that has a max voltage of about 2.1 volts. The pulses of the square wave coincide with the peaks of the original audio signal. This makes it much easier for us to filter the signal with our code. These waveforms are the voltages across the transistors connected to the collector and with respect to ground. Channel 1 is the high-pass signal and channel 2 is the low-pass signal. The transistors act like a switch. When the voltage is high, the transistor is open, and the respective LED will not be on. But when the voltage is low, the transistor is closed, turning on the LED. To close a transistor, a current of at least 45 milliamps must be sent to the base. We measured the current coming from the microcontroller and found that it satisfies this requirement. When both voltages of the transistors are low, then both the LEDs are on, and vice versa.
In conclusion, we were able to build our system successfully by gradual steps by using a microcontroller, speaker, transistors, and LED strip to achieve that.
In this project, we were able to, as a unit, research and develop a digital filter to drive an LED string. Through small steps, we were able to identify and solve problems much more efficiently. By gradually chipping away, we were able to ensure not to overshoot our intended goal. After a successful proof of concept, we continue to strive for a more efficient system.
If we had more time, we could add a bandpass filter to power the third LED on the strip. We could do this just by adding its equation and following the same steps we used for the other two LEDs. A real-world example of this is like a light show at a concert.
Thank you for watching.
Thanks.
Thank you.